Hey there, and welcome to my video on the fundamental theorem of calculus. This is following up previous lessons related to the definite and indefinite integrals, how you actually perform integration by kind of undoing what a derivative would say to do. And so far what we've done is we've kind of integration is essentially what we're looking at, the area problem. This is the second big thing that we would typically think of in calculus. First being the differential, the tangent line problem. Now we're looking at integration, so we're looking at the area. Well, what we've done so far with integration to find an area, we've either been limited to simple geometric shapes that we could find the areas of very easily, or approximating things using Riemann sums. Well, what we're going to get into now is the fundamental theorem of calculus, which actually has two parts that will allow us to find an area under a curve without having to use geometric shapes or approximate things. And kind of what they're saying here, Leibniz, I can never remember how it's pronounced, and Newton, they both made the same realization that differentiation and integration are inverse operations of each other, which is true in so many other aspects of math. It really isn't all that surprising that we would have one here also. So here, differentiation, tangent line problem, definite integration, area under the curve. Here it's just kind of giving it to you symbolically. And let's go ahead and get into the actual meat of what we're talking about here. Pardon me. Given that f, lowercase f, represents the rate, the derivative, at which function f, capital F, the antiderivative, is changing. That is, the function f of x should equal the derivative of the antiderivative, which is a bit of a mouthful. The derivative of the antiderivative should produce or should be equal to the function or the expression that you're using for your definite integral. And what it's representing is here it's talking about this is an idea of the total net change over a closed interval from point A to point B. And it says here if a function f lowercase is continuous over a closed interval and its antiderivative capital F is on the same interval, then the area under the curve is expressed thusly. Okay, like that. That essentially is what part of the fundamental theorem of calculus is getting towards to show you how you can actually get the area under the curve. This bit here on the left side of the equal sign, that is your definite integral. That's your definite integral. And the two pieces over here, the capital F represents the antiderivative. So this is the difference in your antiderivative, where we take the upper bound and subtract the lower bound from it. And it does give you an alternate way of kind of writing it, but I am kind of particular to that method there. So again, the definite integral of a function over a closed interval a to b is going to give you the total change or the displacement of the antiderivative over some function f over the same interval. And this is what we're getting known, or this is what we're introducing to as the fundamental theorem of calculus part 1. Now, in some textbooks, this may be the second part of the fundamental theorem of calculus because there's two parts. And which is considered part 1 and which is considered part 2 is arbitrary. One does not need to precede the other. So what we're going to be looking at for our first idea of what the fundamental theorem of calculus is really this guy right here. so that way we can actually perform some anti-differentiation to get the area under the curve of things that don't have geometric shapes or approximations with Riemann sums. So here at the bottom, we kind of see a different way of writing it, where the two things on the right side are the same idea. Where this bit here is just a different way of showing you what we're going to be taking the difference of. Now here, what they're going to give us next is, or first, really before we get into uh, how the actual process of doing them, is they're trying to give us some real world examples of things that we're doing here. So I'm not gonna make you watch me write everything down. I'll pause the video and have things kind of pop up as we need to. But for time, here they're trying to give us some things in terms of a real world application for how the integral can express the rate at which something is changing. In this case, if f of t represents the rate at which your 401 changes over the value over the month of January, the units f of t, this would be the amount of money per day, where dt represents the number of days that there are, and f of t would represent the money, or f of t dt would represent the money, how it's changing. So looking at the part down here at the bottom, can you understand what it's telling you in this context? It's just basically translate the statement from a math statement to a verbal statement. So here, the lower bound, and the 31 to the upper bound, those are going to represent the number of days in the month of January, because that's what they told us it would be. So here, the way that I would represent this is I would say this definite integral for the situation that they're giving us is going to be the value of your 401k, the value of the 401k in dollars for the month of January. So that's really all they're asking us to do is, can you interpret the meaning behind these real world type scenarios here. So go ahead and pause the video and try doing this one, and hit play when you're ready, and see if your stuff and my stuff match. Okay, so here we go. If R of t represents the rate at which your pizza changes in a 475 degree pizza oven, degrees Fahrenheit, 5 minutes after the pizza has been placed into the oven to cook, how is the what is this definite integral telling us? Well, in this case, it would represent the temperature in degrees Fahrenheit while it's in the oven from the time 5 minutes after you placed it in to 20 minutes after you placed it in the oven. And that's what we are going to be looking at for that one. Here, it's a little bit more of the same thing, but it's kind of breaking it up into different ways of expressing it over some similar intervals. Excuse me. Now, if you notice, they are giving us two different things. We have here A of t, and here we have P of t. And this is kind of a silly thing. Here's the band, the New Tons, and they have this spectacular math titled song here, Why Integrate. And what we want to know is, can you, based on what we've seen in the last couple of examples, understand what we're talking about? Well, here, AFT represents the rate at which students are arriving at the ticket window. So looking at this first integral here, from 1 to 5 AFT dt, that's going to represent the number of students. So number of students arriving to get in line on the interval from 1 to 5 minutes. And I'm almost out of room, 1 to 5 minutes. And so P of T, it tells us in the problem that P of T represents the rate at which they buy their tickets and enter the concert. Okay, well, if they buy their ticket and and I don't know who stands in line to buy a ticket anymore, but here P of T would represent the number of students who already bought their ticket, or who have bought their ticket after standing in line, ticket, and then leave the line, which makes sense. Leave the line on the same interval from 1 to 5 minutes. You know, because you stand in line between the time from 1 to 5 minutes, and you buy your ticket, you leave, right? You go into your venue, or you go check out the merchandise, see what kind of t-shirt you want to buy, stuff like that. So here, between A of T and P of T, where remember A of T is representing the rate at which students are arriving at the ticket window, and P of T represents the rate at which they buy their tickets and then go into the concert. Here, A of T minus P of T, that is going to represent the rate at which the line is growing and shrinking. So the rate at which the line grows and shrinks. You know, because here, A, we're arriving, and P, we're purchasing our tickets and then leaving. So the final integration here in part 4 of this example, C, the definite integration of A of T minus P of T dt, and sometimes you may see it in kind of parentheses like that, represents the total change in what? The length of the line of the students, in this case, the length of the line of students on the interval from 1 minute to 5 minutes. Now here, this is kind of going back to things that we have seen previously in calculus with position, velocity, and acceleration. They're not really going to go away. And here, recall that velocity, v of t, represents your velocity, where positive direction is to the right. So here, filling in the blanks, velocity is a rate at which the position of the particle is going to be changing. Here, the definite integral from 5 to 50 of vt dt represents the total change, in this case, of position uh, on the closed interval 5 to 50, whatever that is, minutes, seconds, whatever, which has a special name in math. And again, this is the overall change of something over the interval. That would be displacement. Displacement. And likewise, a of t, that's going to represent the acceleration. A of t is the rate at which velocity changes. So if velocity represents the rate at which the position of the particle changes, then acceleration is the rate at which velocity is changing. Because remember, the derivative of the position function gives us the velocity function, and the derivative of the velocity function gives us the acceleration function. So here, this is just a little graphic that is in the presentation to represent how we're kind of estimating the area under the curve. And now it's actually time to, not so much interpret the meaning of the integration, but actually perform the integration using the part one of the fundamental theorem of calculus. So here, what we would look at for the first example, depending on how you want to look at it, we can say here, like f of b minus f of a, based on what we saw for the, fundamental theorem part one, we would say like that. Or you can look at it as the antiderivative as it is evaluated from b to a, something like that. Whichever way you prefer, as long as you understand that we need to find the antiderivative of the integrand and then substitute the numbers that are given to us into the antiderivative and take the difference of them. So in this case, from 3 to 1, we have x cubed dx. Well, the antiderivative of that is going to be, what would that be? 1/4 x to the 4th power. And of course, we're not going to add the c here because this is not an indefinite integral. This is a definite integral, so we don't need a constant of integration. Okay, so here, this is, f of x, like so. We have the antiderivative. This is what we're going to now be doing our, plugging and chugging with. So here I'm going to say 1/4 times the upper bound, 3 to the 4th power, minus 1/4 times the lower bound, 1, also to the 4th power. And in this case, or if you want to, you could recognize that the 1/4 is a constant, and you could say 1/4 times 3 to the 4th minus 1 to the 4th, or just 1/4 times 3 to the 4th power, however you want to think of it. And when you work it out, we're going to get this bit here. So here we're looking for the area under the curve. The antiderivative here. And we're going to get a value of the first one. I just did it on a calculator. I got 20 1/4. And then 1/4 times 1 to the 4th is just 1/4, 0.25. So that gives me a 20. And that would be the area under the curve, the definite integral, the answer for that particular problem. Okay, Now, there are quite a few of these, so I'm not going to necessarily work all of them out. I'll just pause the video and put things up here for some of us, for some of them. But feel free to pause the video and try to work some of these out. If you're following along with the notes, there's 2, 4, 6, 8 of them for practice, and they're going to vary in level of difficulty because we're going to have, you know, certain things for just different kind of integrands to make sure they're not going to all be homogeneous. They're not all going to be done the same way as far as the antiderivative is concerned. But here, looking at this one, the antiderivative, and I guess we'll just kind of keep it as f of x. The antiderivative here is going to be, what do we have? We're going to say 1/3 x to the third power minus 3x, and we're going to be evaluating it from 2 to 1. So here I'm going to say 1/3 times 2 cubed minus 3 times 2 minus, and then we'll say 1/3 times 1 cubed minus 3 times 1, and see what we end up with here. So here we get 8/3 minus 6, and then we're going to say minus, and inside of the brackets here, I'm going to get 1/3 minus 3. So looking at these two fractions here, that would give me, let's see, multiplied by 3, 18, 8 minus 18 would be a negative 10/3, and then minus here, 1/3 minus 2/3 would be negative 2/3, so that'll actually be plus 2/3, and nope, I'm not doing that right. I did that backwards. I did it in my head as 3 minus 1/3 instead of 1/3 minus 3. That's actually going to be, what would that be? Times 3, negative 9/3. So that would be negative 8/3. So that would be positive 8/3 when I distribute the negative sign in. So overall, we get a negative 2/3. Okay. So let's move on and see what we have here. Now, I want you guys, whoever's watching the video, go ahead and pause it now and see if you can work these two out. And I'm gonna do the same. I'm gonna pause the video and then work it out, and then you hit play and see how you did. See how your work compares to mine. So go ahead and try it now. And when you're done, hit play. Okay, hopefully you did what I asked you to do, and you were able to identify what the uh, value of the definite integral is going to be. So on the left side we got a 14, on the right side we got a 1. Hopefully you were able to, particularly with secant squared, recognize that the antiderivative of secant squared was just tangent, and you remember your values off of your unit circle for that one. And same thing here. We got a couple more problems here, and again I'm going to ask you to go ahead and pause the video, work them out, see if you can get the answers ahead of me, and I'm going to do the same. I'm going to pause the video and work them out, and when you're done, hit play and see how your work compares to mine. All right, and here we have the next two examples worked out. The way I looked at E, I didn't want to try to do the antiderivative using the, like if I leave it the way it is in factored form, I think it was going to be a little bit more complicated than it would have been to just expand the function, to expand the integrand to put it in standard form. So I'm looking at it with 4x squared minus 4x plus 1 dx. And again, I probably should have all of that in parentheses, but I mean, you put it in parentheses, you don't. I think after a while, pretty much everybody understands what you're doing. And once I've expanded the binomial, I will take the antiderivative of that to get 4/3 x cubed minus 2x squared plus x, and I'm evaluating it from -1 to +1. And so plugging those values in, +1 first into the entire function. Make sure that you always subtract, when you subtract that lower bound part, remember to put it in parentheses to keep your sign straight with the negative on the outside. When you're subtracting an expression, so you have to put the expression in parentheses. And I wind up getting a 14/3. On the right side, the antiderivative of sine gives me negative cosine, and the antiderivative of 1 will give me a 1x. And we're evaluating it over the defined interval or the closed interval from 0 to pi, and plugging in the upper bound and subtracting the lower bound, in this case using the fundamental theorem of calculus that we've been doing, would give me an area, the defined interval, the defined integral, not interval, would be 2 plus pi, whatever that works out to be. And here's our last two. And again, I'm going to encourage you to go ahead and try pausing the video here and see, can you work these out? And then when you're done, you can hit play and the answers will magically appear on the screen and you can see how well you did, or how your work and my work compares, and make any adjustment you need. So go ahead and pause the video, work these out, and then when you're ready, hit play. All right, here is the last general kind of practice problems that we're looking at for what we've so far identified as part one of the fundamental theorem of calculus. What I'm doing with the problem on the left, G, is I'm using properties of exponents to rewrite the integrand as square root of 2 times x to the -1/2 power, because that is what we're going to use as the when we do our anti-differentiation. And depending on how you wanted to write it, I kind of wrote it out three ways. I said you could say 2 radical 2 times x to the 1/2 power. You could have 2 radical 2 times radical x, or you could combine the radicands and you could say 2 times square root of 2x. Either way that you wrote your antiderivative, one of those three things, you should still wind up with the same value when you do your substitution, with the upper bound minus the lower bound as 8 minus 2 radical 2. The problem on the right, I am kind of separating the fractions so I can simplify the first part of the fraction as x over x to the 1/2 power. So that simplifies to be x to the 1/2 power just in the numerator. And same thing on the right side, the separate second fraction, I'm going to just move the x to the 1/2 power to the numerator, changing the sign. So my integrand, I'm just rewriting it to be x to the 1/2 power minus 2x to the -1/2 power. Take the antiderivative, and I get 2/3 x to the 3/2 power minus 4x to the 1/2 power. And we will be evaluating it from the interval from 1 to 4. So substitute the upper bound first into the function, subtract the function with the lower bound substituted into it, and it works out to be a 2/3 positive. So hopefully we're understanding that stuff okay, and it's not going to be too difficult. But if you have any questions, of course, let me know. Now we're going to be taking a look at the second part of the fundamental theorem of calculus. And I don't want to get too much into the graph here. You're welcome to kind of read it and make your interpretations of it as you want to, but I want to get into the idea here. Okay, so let's get into the actual meat of it. Essentially, what the second part of the fundamental theorem of calculus is going to tell us is that the derivative of the antiderivative should equal the integrand, whatever the expression happened to be. So we have this definite integral, and one of the things that we notice here, this is where we're really starting to get into the second part of the fundamental theorem of calculus, is if you notice, one of the either the upper bound or the lower bound are not going to be a constant value. It's going to be an expression of some kind. And so what we do is if we take the antiderivative, what it's telling you, use the fundamental theorem of part 1, along with the fact that f of t is equal to 1/3 t cubed is the antiderivative of t cubed, we can find the particular solution of this problem to be 1/3 x to the third power. Now, obviously, if I take the derivative of that, if I take the derivative of this, that would give me 1x squared. So this is the antiderivative. Well, if I take the derivative of the antiderivative, I basically get the same integrand that we started with. And that's kind of what we're talking about for the fundamental theorem of calculus. That's not always going to work out to be the same thing. And that's what we're going to be looking at. So here, it's kind of illustrating what I just said. Since the antiderivative was this, if I take the derivative of the antiderivative, I wind up with this, which is essentially what the integrand was at the beginning. Of course, the variable switched from t to x, but if you're just thinking about them in terms of an input, they're basically the same thing. Okay. So here, given that the antiderivative f of x is equal to the integration of the expression f of t dt, f of t has always been the derivative of the antiderivative f of x. However, this is not always exactly the same the case. So what we're going to show you using the fundamental theorem of calculus part 2 is going to be something a little bit different. Okay. Let's see, because I don't know if I wanted to do anything with this here. What we're seeing here, this is just again the derivative of the antiderivative. Okay. That's what the fundamental theorem of calculus is going to say, is that it should put us back to whatever f of t happens to be. So, but unfortunately, that's not going to work out to be the case all the time. And what we want to be able to do is identify, well, how could I find the derivative of the antiderivative if they don't always equal the integrand? Okay, so let's see. I don't think there was anything I wanted to add to here. So here, this is what I have, in my mind as far as what I'm thinking when I see this. This is what I'm thinking here. Does the derivative of the antiderivative equal the integrand, but we'll say it's as f of x instead of f of t. Okay. So that's what we're trying to establish. And there's a few problems that we're going to look at here to identify it. Now, if you're following along with the notes, this bit here, I moved it up in the presentation a little bit because I think it makes more sense here. Because this is what the fundamental theorem of calculus part 2 is ultimately going to tell us, and we're going to get there, okay? But for the time being, I just wanted to put this out here first. The derivative of the antiderivative, that's what this is saying. This is the derivative of the antiderivative. It is going to be equal to the composition of f of g of x times the derivative of whatever g happens to be. Okay, and of course, the g of x part, that's the upper bound of the definite integral. So we're going to come back to that. I just wanted to put that out here first because I think it makes more sense to introduce you to say, hey, this is what it is, rather than for us to try and stumble our way to drawing that as a conclusion. So just bear with me here. All right. So here, this is our first case. What it's asking us to do, it says we want to find essentially the derivative of the antiderivative. So let's find f of f, capital F of f, x, I mean, okay? So here, the antiderivative of cosine is just going to be sine. So here I'll say sine of t from pi to x. So using what we did in the fundamental theorem part 1, we're now going to say sine of x minus sine of pi. Sine of x is just sine of x. Okay, but sine of pi is 0. So we wind up with just sine of x. That is the antiderivative. Well, if I take that, what is the derivative of the antiderivative? What's the derivative of sine of x? Well, it puts me back at cosine of x, which matches what we had there. And that is essentially what the fundamental theorem is trying to make us understand, or at least part 2, I should say. The derivative of the antiderivative is equal to the integrand, or f of x, whatever it should be. Okay? And I'm sorry, I probably should have put it here on the right-hand side where we have f prime of x, but I'm gonna probably use the right side of that, or the right side of that screen, because I want to come back to this. So now let's take a look at case number 2 in the notes. Okay, same idea. We want to find the derivative of the antiderivative and see what we wind up with. Okay, so let's work it out here. Okay, the antiderivative in this case, the expression, will be 2/3 times 1 plus t to the 3 over 2 power, and we're evaluating it from 0 to x minus 3. So again, we're going to take the upper and lower bounds and substitute them in there. And let me move this over a little bit because it's going to take up a little bit more space horizontally now. So here we're going to say 2/3 times 1 plus, in this case, x minus 3 to the 3 over 2 power. And then we're going to say minus the 2/3 times 1 plus 0 to the 3 over 2 power. And see what we end up with. So here we get 2/3 times x minus 2 to the 3 over 2 power. And the second part is just going to be minus 2/3. Okay, so that is the expression of the antiderivative. Now again, I'm not going to use the space on the right side here to illustrate. I'm going to use the space on the right side to come back shortly and say, okay, well, what is the derivative of the antiderivative? We're using the power rule on the first bit. We're going to wind up with just x minus 2 to the 1/2 power. The derivative of the constant is 0, or I can write it as the square root of x minus 2. And if you notice, this and this, they don't match. Okay? And the idea is what the fundamental theorem of calculus is going to try and get us to is how can we go from this right to that? Okay, how are we going to do that? And this is one of the things I want to come back to. So there's one more example that we're going to take a look at real quick. Again, find the derivative or the antiderivative first. So capital F of x, in this case, I'm going to get the expression to be 1/3 p cubed evaluated from 4 pi, which is just a constant, to cosine of x. So do your substitution the way we did on those 8 examples. Put in the upper bound first. So I'm going to say 1/3 times, in this case, cosine cubed of x. And then we'll say minus the 1/3. And in this case, it would just be 4 pi cubed. 4 pi cubed. So that's the expression that we would have. Now you could simplify the value on the right, but I'm not going to bother with it because again, at this point, we were checking what is the derivative of the antiderivative. So here I'm going to say the derivative of the antiderivative based on what we have. Here, now we do have to use the derivative of 1/3 cosine x squared. So here, we don't need to use the chain rule necessarily, or yeah, we do need to use the chain rule. Let me get that straight. So the derivative of the whole thing, of the 1/3 cosine cubed of x, that is just going to be cosine squared of x. And the chain rule says we have to take the derivative of the inside bit here, so that would be negative sine of x. And the derivative of the constant is just 0. That's why I didn't bother wanting to simplify that one, because the derivative of the constant is 0. So here, we probably write it as negative sine of x times cosine squared of x, or negative cosine squared of x times sine of x, however you wanted to do it. But clearly, this and this don't match. Okay? So now I want to go back a little bit, and I want to say, okay, well, what are we looking at here? What do we really want? And this is where I want to reincorporate this expression. The derivative of the antiderivative is equal to the composition of f of g of x times the derivative of g of x. So now let's go back and let's reevaluate these same problems. And so here, I guess I'll go ahead and go back to the blue color. And so here I'm going to say, and I'm going to go ahead and just write it down, f of g of x times g prime of x. Okay? So in this case, f is cosine of t. So using my composition rules, I'm going to say cosine of g of x, which g of x is just x, so cosine of x, times g prime of x. Okay, so times g prime of x. And in this case, the g prime of x is just 1. So we wind up with cosine of x. And you see here, this is where we're going to. This is, even though this one matched, okay, this is still the derivative of the antiderivative. Okay, but did we need to go through all of this stuff here in purple to get there? No, we didn't. Okay, and this is why I wanted to introduce you to, I wanted to put the rule up there first so you had the rule rather than us trying to interpret that rule for ourselves or intuit that rule for ourselves, because I don't think I could have done it. So here again, now we know what the antiderivative the derivative of the antiderivative should be. So now let's see, can we get it? So let's go back to that green color, and I'm going to use my my rule now, where I'm going to say f of g of x times g prime of x. And of course, this guy right here, the upper bound, that is g of x. So here, f is the square root of 1 plus t. So I'm going to start with the square root of 1 plus, but now we do our composition. So anywhere I have t, I'm going to put the g of x expression, which in this case was the x minus 3. And the derivative of the g of x expression, the x minus 3, so the derivative of g of x is just 1. So the radicand simplifies to be the square root of x minus 2 times 1 is just the square root of x minus 2. And so there we go. The derivative of the antiderivative is now found using that little rule. It looks very much like what we would say for the chain rule, except we're not taking the derivative of the whole thing. We're just doing a composition multiplied by the derivative of whatever the upper bound happens to be. So see if you can do it here. Prove it to yourself and see what you end up with. Let's go ahead and go to that same color for the antiderivative so we know what the conclusion should be because we did our work for it already. And again, I'm going to just write it out because personally I think anytime you use a rule, you should write it down because it helps you memorize it and remember it when you need it. So in this case, we're going to say t squared, which is the f part. The t squared is the f part, and we do our composition, so that puts me right at the cosine squared of x. And the derivative, and remember the upper bound, that is your g of x. The derivative of that is the negative sine of x, which puts me right back to negative sine of x times cosine squared of x. So we're able to get the derivative of the antiderivative using that expression, should we need it. So here I want to see, can you do it on your own? Okay, can you predict what will happen? Basically, it's asking you, can you get the antiderivative or the derivative of the antiderivative? Can you get that from here? So go ahead and work it out, and when you're ready, hit play, and the answer will magically appear on the screen. So how'd you do? Finding the derivative of the antiderivative using the second part of the fundamental theorem of calculus. Hopefully, probably the simpler way of writing it is the way that I have it written on the right at the bottom, the 2x times e to the x fourth power. But either one of them would be fine. And now here, this one is kind of, it's straying from the path a little bit. It's still talking about finding the derivative of the antiderivative, but in this case, it's not going to give us all the information that we need in order to really find the derivative of the antiderivative. This is more of a traditional type of algebra problem than anything else, where instead of giving you all the information up front, where you can just kind of plug and chug away, you got to work backwards a little bit. And this one in particular, you need a calculator for. Now, the reason why I'm telling you that they're not giving us everything that we need, it's asking us to find f of 2. So they're not giving us the entire information that we need for our fundamental theorem of calculus. So let's see what we have. We have our lower bound at x is equal to 1. We have our upper bound at x is equal to 2. And they're giving us an integrand. So we can write the definite integral here of 1 to 2 e to the negative x squared power, and again dx, and using the fundamental theorem part 1 that we were looking at, we can rewrite that, or we can think of that as f of 2 minus f of 1. Okay, so find f of 2. So what we want is we want to find that piece right there, meaning we don't know what that value is going to be. All right. So the part here on the left, this is where we need our calculator. And if you're not sure how to do the definite integral on the calculator, you may need to look it up or come ask for help, something like that. But the definite integral in this case will work out to be about 0.135. And we're asked to find f of 2, so I'm going to just leave that as f of 2. And it tells us that f of 1 was 3, so minus 3. And so now you move the 3 from the right side to the left side, and we get 3.135 for f of 2, the antiderivative of the upper bound. And that's what we're looking at on that one. Now this last bit here is going to incorporate some things with a table, where we're going to be looking at it, with a table and kind of graphically. This last example, let f be the function whose graph is below. Use the graph of f and the fundamental theorem of calculus to answer the questions about it. So complete the table of values for f, and let's go ahead and and I think I'm gonna, you guys go ahead and start filling this in. Pause it if you need to, so you can kind of watch it as you do it, but I'm gonna resize these here real quick. Oh, I thought I had paused the video while I was doing that, so sorry. Uh, Live and learn. So I just wanted to resize it so it was easier to work with. I thought I paused the video and I did. All right. Let's go ahead and start plugging in some things here, see what we get. Uh, Hopefully I didn't do anything or say anything inappropriate while I had the video paused. Okay, so filling in the table, they're giving us basically the intervals that we're working with. So here, when x is 0, looking at the graph, we're not moving horizontally at all. So the area under the curve, and we're using simple geometry here, the area under the curve here, if we don't have any horizontal motion, the area is 0. Moving to 1, and I guess we can kind of keep doing these in different colors. So when I move to 1, we're looking kind of at this area of the triangle here. So that will work out to be base times height divided by 2 will be a 1 in this case. And we just kind of keep going, accumulating the area. So the next bit here, when we go from, then we can kind of keep adding. This is going to get convoluted if I try to do all of them. Let's do kind of a yellow one. Now we've gone to this 2 here. So we can take the area of the triangle that we've added, and then we can just add the area of that rectangle. Otherwise, we can kind of think of this trapezoidal region here where I have a base of 2 here, a base of 1 here, and a height of 2. And that will work out to be an area of 3. And let's just go ahead and fill in the rest here, just so that way we can have them. So the next one, from 0 to 4, and the reason why we're doing it from 0 to 4, remember, or we're starting at 0 each time, is because pay attention to what the lower bound was. That's why we're starting at 0 and just kind of keep going to the right. So here I'm going to get a 4, here I'm going to get a 3, and here I'm going to get a 2. Okay. And again, keep in mind anything that is below the x-axis representing negative area. That's kind of why we're seeing the value decreasing over that interval. So let's see what we have here. So plot the points on your table to complete the graph of the antiderivative. Okay, well, let's go back and do that there. So if I go back and I, kind of take the points just, directly from the table, let me go ahead and clean this guy up a little bit. So we have some space, and let's do it in blue, I guess. So we have 0, 0, we had 1, 1, 2, 3, 3 and 4, 4 and 3, and then 5 and 2. So we're going to have something like this. Every time I do stuff like this, I don't know if they still do it on The Price is Right, but they used to have like some yodeling kind of game on The Price is Right, and when you're home sick from school, you always get to watch The Price is Right, and they go yodeling, it's kind of something like that. And I always think like, for some reason, it always goes through my head when I'm kind of drawing those graphs like that. Anyway, I know I'm a goofball. So we plotted our points. Where is the 0 of the antiderivative? Well, that was at the origin. It was at 0, 0. That's the only place it touches the x-axis at. What is the total net change? So here, if we looked at it, the total net change would be f of 5 minus f of 0, which if we take those values, that would be 2 minus 0, which would be a 2. Last 2 here. How does the total change in the antiderivative compare to the net area bounded by the graph of the function f of x and the x-axis? So here, since the antiderivative, they should be the same. That's the simple answer. Let me try and I have a convoluted explanation in my head. Let me go ahead and write it down. Since the antiderivative is equal to the definite integral 0 to 5 of f of t dt according to the fundamental theorem of calculus, the net area of the antiderivative is the same as the area bounded between the function, the function and the x-axis. So the maximum value of f of 4 of f of x was at when f of 4, so that's what we're looking at here. And when will it occur? When x is equal to, when x is equal to 3. And that, ladies and gentlemen, is going to wrap up the presentation that we have for the fundamental theorem of calculus, parts 1 and 2. Part 1, the way it was demonstrated in this lesson, is going to be very useful for a lot of things, because we're not so much always going to be looking for the derivative of the antiderivative. We want to know what's the area of the curve, and that's essentially what that first part of the lesson was talking about. But if we do need to find the derivative of the antiderivative, we can use that formula, the composition of f of g of x times the derivative of g of x. Hopefully you found this information useful, because this will be something that you use in a lot of aspects for calculus when you're doing integration. But thank you guys so much for watching. Hope y'all are doing well. Take care, and we'll see you soon.